Have you ever witnessed a cheetah run? It's a spectacle of nature, pure speed, a flash of spotted fur and straining muscle. These animals are the planet's sprinting champions, but what is their secret? Look closely at their remarkable legs. The cheetah is an evolutionary marvel. Its very survival often depends on these quick bursts. Every part of its streamlined body contributes, especially those uniquely adapted, amazing legs. You'll notice they are not bulky or heavy. They are exceptionally lean, particularly the lower parts. This striking design isn't exclusive to cheetahs. Many other fast animals share this anatomical feature. Think of graceful gazelles or sleek greyhounds. Their lower legs are also notably slim and delicate. Let's embark on a journey to explore this natural wonder. Let's imagine two fundamentally different leg designs. One is structured much like a cheetah's leg. It is long, elegant, with a very thin lower section. The other is more like a human leg for comparison. Our own calves possess significantly more muscle mass. More weight is therefore distributed further down towards the foot. Or, for another contrast, think of an elephant's sturdy pillar-like leg. Clearly, these are different forms sculpted for vastly different needs. Now, in your mind, try to swing these imaginary legs. Swing them back and forth. Which one of them feels considerably easier to move? It's the one with less weight concentrated at the end. The precise distribution of mass fundamentally matters. It's not solely about the total weight of the leg. What's truly critical is that weight is located. Is the bulk of the mass situated close to the hip, or is it positioned far down, near the ankle or foot? Fast animals, through eons of adaptation, seem to understand this. Let's dive deeper into this fascinating physical concept. Moment of inertia. Does that sound overly complex? It's not as intimidating as it might seem. You can think of it simply as rotational laziness. It describes how much any given object resists spinning, or how much it resists a change in its current spin. If an object is already spinning, how hard is it to stop? If it's perfectly still, how hard is it to get it started? Let's use a familiar and helpful analogy. Consider an ice skater. They spin gracefully on the ice, arms extended, they spin slower. Then they pull their arms in tightly and they spin much faster. They expertly changed their own moment of inertia by strategically pulling their mass closer to their axis of rotation. The very same principle applies directly to legs in motion. A leg, for the most part, swings from the hip joint. That hip joint acts as the primary axis of rotation. So what happens if the leg's mass is concentrated near the hip? The moment of inertia for that leg becomes small. It becomes significantly easier to swing that leg rapidly. This crucial ability allows for more strides per second. And now let us return our focus to our star, the cheetah. Its lower legs are astonishingly light, almost delicate. They consist of thin bones with minimal muscle mass attached. So where are most of its powerful leg muscles located? They are positioned up high, very close to the main body, concentrated near the pivotal hip joint, the axis of swing. This specific anatomical design masterfully minimizes moment of inertia. This clever arrangement allows for an astounding leg turnover rate. The cheetah can reposition its long legs with incredible rapidity, swinging them back and forth, a blur of motion, at a frequency that we humans can only dream of achieving. Each individual stride it takes is both long and immensely powerful, and it can take so many of these strides so very fast. This is the core mechanism of its explosive acceleration, enabling it to reach its phenomenal top speed in mere seconds. Our lower legs are comparatively heavier and bulkier. Our calf muscles, for instance, are quite substantial and powerful. We are simply not built like cheetahs for raw speed.